Good afternoon and welcome back to the 22nd Annual CERIAS Security Symposium live from Purdue University. It's my pleasure to introduce our first technical talk of the day. Jin Wei-Kocsis is an assistant professor in computer and information technology. Her research focus includes deep learning driven security and privacy for cyber-physical social systems and blockchain powered IoT enabled secure and privacy preserving crowdsourced computing paradigms. Jin, good afternoon.
Sorry, I'm mute. And thank you very much for the opportunity for sharing some of our work in our research lab. Today, I would like to present some of our work on deep learning powered situational awareness for securing cyber-physical critical infrastructures. Due to the advances of sensing, computing, and networking, more and more cyber components and physical systems has been combined with each other for different operations in different critical infrastructures, such as smart manufacturing infrastructure, smart energy system, and smart transportation systems. Those tight cyber-physical coupling dramatically improve the effectiveness and efficiency of the different operations in those different critical infrastructures. However, at the same time, it also raises a series of unfamiliar attack surface and results in the increased vulnerability of the operations to the potential cyber attacks and physical failures. Different research and solutions have been developed effectively to mitigate those cyber-physical attacks in those critical infrastructures in order to enhance the security and the resilience. However, there still remain some challenges in the real application operations. So those kind of challenges have been demonstrated in the different real-world attacks occurred nowadays. For example, in 2015, there's a cyber attacks occurred in the power system in Ukraine. This power system has resulted in a large-scale power outage. This attack was launched on the computer and the SCADA system of the regional electricity distribution company and resulted in the disconnection of 7 substations for 3 hours and forced operators to switch to manual mode. So there's another attack occurs in the water treatment facility in Florida in 2021. Due to the investigation, this attack occurred about 15 miles away from the location of the facility and 2 days before the Super Bowl. This cyber attack managed to adjust the levels of sodium hydroxide from 100 parts per million to 11,100 parts per million. Luckily, this attack was averted and terminated by the operator of the facility in time. We can imagine if this attack succeeded, we can potentially cause very severe safety-related accidents. So we can see it is really emergent and it's very critical to achieve or improve the security and related solutions in order to enhance the resiliency and the security of the critical infrastructures. In the light of those challenges and demands, our cyber-physical social system design lab aims to leverage the deep learning technology to provide and achieve the deep learning powered situational awareness solutions for securing the cyber-physical critical infrastructures. So in this talk, I would like to present some of our work aligned with 3 research directions. First, deep learning-based architecture for detecting cyber attacks and physical failures. Second, attack-resilient communication infrastructures. And last, bio-inspired intelligent decision-making and control. So first, deep learning-based architecture for detecting cyber attacks and physical failures. Thanks to the advances of sensing and computing, deep learning techniques have been widely and successfully applied in the security domain and provide a series of promising solutions for achieving a timely situational awareness. However, there still remain some essential challenges to achieve the more practical solution for addressing the real-world problems. For example, the security-related data is very limited, especially the ones associated with some rarely happened security-related incidents. And also those data is sparsely labeled because labeling and achieving annotation of the data can be very time-consuming and labor-heavy. And also, in recent years, many evidence have been shown that the decision-making of the machine learning model can be misled and because of some carefully crafted perturbation or adversarial perturbations. In order to address those challenges, we provide, or I talk about two solutions have been provided in our research lab. First, a hybrid weak supervision-based method by exploiting human domain knowledge, and second, blockchain-enabled decentralized secure situational awareness system. The first, the hybrid weak supervision-based method. This aims to address the first challenge, the scarcity of labeled data. This architecture provides an overview of our proposed method. We can see here consists of three main learning models: primary learning model, secondary learning model, and latent feature learning model. The primary learning model is designed aim to extract the features from the limited labeled data and interact with other two learning models. The second learning model is designed to interact with the primary learning model and to extract the critical features from the unlabeled data that is consistent with the features from the labeled data. And the latent feature learning model is the critical component in our work. It's aimed to interact with the primary learning model and the second learning model accordingly in order to seamlessly integrate the domain knowledge with the cyber features presented by the data directly. By doing that, we are able to achieve appropriate and reliable decision-making for situational awareness, even the system only have the limited data, has a very limited, or we say sparsely labeled. And we also provide another solution, blockchain-enabled decentralized and secure situational awareness system. This one aims to address the other two challenges. First, the lack of valuable data and security of machine learning. So this one provides an overview of our proposed structure. So the main idea here is we design this blockchain-enabled decentralized cooperation architecture so that the different computing units, they can have very limited computing power, limited data, and even untrustworthy to each other, but they are able to collaborate with each other in a secure and privacy-preserving way to solve the associated task. So those computing nodes can participate in this collaboration by playing one of the three functions: application initiator, computing contributors, or verification contributors. If the nodes or the computing units play as application initiator, it will announce the learning-driven or data-driven situational awareness task via this blockchain-based middleware, and they will specify their objectives and constraints of the task via the blockchain smart contract and submit the necessary training and testing data in the decentralized and secure data storage systems. And the computing contributor, if they would like to participate in this task, they will train their local learning model based on their private local data or the data shared by the application initiator according to the objectives and the constraints shared by the application initiator via the blockchain smart contract. After those local learning model trained and claimed via the blockchain-based middleware, the randomly selected verification contributors will conduct the quantitative verification procedure to evaluate the trustworthiness of the claimed local learning model and inform the application initiator with their decision-making. If the majority of the verification contributor have the positive decision-making, the transaction of this local learning model will be established between the associated computing contributors and the application initiator. And after achieving the local learning model from the different computing contributors, the application initiator be able to conduct multimodal fusion mechanism to achieve the meta model to solve those challenging situational awareness tasks. This work has been developed in a NASA project. And in this project, we are able to establish a hardware in the loop prototype for this architecture and evaluate the performance in the NASA deep space exploration task and other related tasks. And the performance is satisfactory. And currently, we're still working on improving the performance and efficiency. So another research is about the attack resilient communication infrastructure. We know the resilient communication infrastructure is very critical for maintaining the appropriate operations in different critical infrastructures. However, sometimes it can be challenging to directly leverage the established communication infrastructure, which were originally established for the other commercialized purpose for maintaining the operations in the critical infrastructure. Here, identify two of the challenges. First, due to the different operating conditions, we may need the tremendous amount of sensing and operation data, and the delivery of those data may need a different quality of service, or called QoS for short, and the quality of experiences, or called QoE for short requirements. Second, we also need a resilient autonomous networking management, even in the presence of certainty. This is because of the complexity and the critical property of the critical infrastructure operations. And to address those challenges, we provide two solutions. First, attack resilient networking middleware mechanism. Second, blockchain-powered multi-controller software-defined network-based networking architecture. First, attack resilient networking middleware mechanism. Here show the overview of our architecture. We can see in this work, we develop a deep learning enabled middleware architecture, which is able to upgrade the established communication infrastructure with a low retrofitting cost and meet the requirement of operating in the critical infrastructure, such as power systems. As shown in this diagram, our middleware is able to monitor the QoS and the QoE demands of the associated operating conditions and evaluate the operation condition of the networking in real time. And then they are able to achieve a hierarchical and intelligent the cross-layer operations of the communication infrastructure. And by leveraging the deep learning technique, we are also able to detect the potential attacks, such as integrity attack in the real time, and then realize the mitigation strategy accordingly. So this work is developing a QoE project by collaborating with the National Renewable Energy Lab. We are able to develop a large-scale and hardware-in-the-loop testing system to evaluate the performance of our developed middleware mechanism for securing the communication infrastructure for a large-scale power system with a high penetration of PVs. So another solution is blockchain-powered multi-controller software-defined network-based networking architecture. The overview as the following. We can see our networking is realized and managed by multi-controller SDN layer, and the multiple controllers will collaborate and operate with each other via a blockchain-based layer. And this layer ensures the security and autonomous management of the collaboration. So our proposed networking management is able to deliver the functionality of integrity verification. So here shows some details of mechanism in order to meet this goal. So we can see if the controller 1 wants to send a command to the controller N, before they send, or instead of sending that directly, they will generate a combined hash value based on the time step of generating of this command and the content of a command. And this hash value will be archived in the blockchain middleware. And then when the controller N receives the command, instead of directly deploying the command, they will also generate the hash value and compare with the ones archived in the blockchain-based middleware in order to verify the integrity. So by using the functionality of the blockchain smart contract, we're also able to realize autonomous detection of malicious hosts to improve the security and autonomous bandwidth provisioning to improve the responsiveness and reliability of the networking management. So the last work I want to provide some overview about is the bio-inspired intelligent decision-making and control. So here our work try to answer two essential questions. First, in order to realize the trustworthy situational awareness. How can we dynamically modeling the complex cyber and physical systems? Second, how could heterogeneous cyber physical components be able to cooperate for securing the operations? In order to answer those questions, one of our work is to develop a flocking-inspired multi-agent resilient control. This research developed by considering the microgrid is one type of a smart energy system as a concrete application domain. So in this work, we're leveraging the flocking philosophy, which comes from the biology area, to formulate the coupling, the cyber-physical coupling between the different components in the microgrid. And based on this coupling modeling, we are able to generate a flocking-inspired reference model whose output will be established, expected normal states of the individual components in this system. And then another reinforcement learning-based situational awareness mechanism is able to monitor and detect abnormal situation by comparing the real situation and with the expected states generated from this reference model, and generate autonomous and secure operation accordingly to maintain the stability of this microgrid. So after providing this some of our works overview, I would like to end with my talk by providing this final remarks. The main idea here I want to say is, but in order to provide a resilient situational awareness for securing the critical infrastructure, it's difficult to only focus on one layer, such as application layer, communication layer, or the physical layer. We really want to secure those different layers in a collaborative way, because in the application layer, they're able to provide sensing and measurement data. They really like the leaves of the tree because they directly interact with our situational awareness, provide those data evidence. And the communication infrastructure is like the branch. It's really connect with the leaves and the trunk of the tree. So, and the last, the physical system, because we really interact with the system physical layer, and also potentially will result in the safety critical situation if we not operate properly. That's why that layer is very essential. So my work and our research lab work is focusing on how to integrate these three layers in order to provide a promising solution. Thank you very much.
Professor Kocsis, thank you very much for that presentation.
Thank you.